So today's problem is 416 partition to equal sums. The example is given an array of 4 numbers, 1, 2, 5, 2, and we want to partition them into 2 groups such that the sum of them are equal. So in this example, we can see we can use these 3 numbers as one group, and this one as another group. So this one will be 1, 2, 2, having a sum of 5, and this group also have a sum of 5. Then the observation is that if we can simplify the problem into finding just one group of numbers with the sum half of the array sum. Exactly. Just find one group of numbers. Let's have array. And the way is that we can try each element, whether we want to select this, and then we try whether we want to select the second number, and then we will try whether to select all of the numbers, and one of them will definitely give us the correct answer. And so the idea of dynamic programming is just to try whether we want to select it or not selecting it. And we will test if selecting it will give us the optimal answer. So let's draw a dynamic programming table. For this row, we will say that. So the idea is taking the first I elements, take first I elements, and whether we can satisfy the target sum. Take the first I elements to satisfy the sum. Satisfy the target.
Right.
Target J. So we have. If we begin with. So here the total sum is how many?
It's like 10.
Yeah. Thank you. So the target of the half of the sum is 5.
Yeah.
Yes,
And
exactly.
you can also like check mod2. It's like if the total sum is like 11, like it's not even. So.
Yeah, that's a great suggestion. We can optimize it by check whether it's even or odd, or check whether mod2 can work. Yeah, that's a great idea. Then we will, so the target is 5. We only need to check from 1 to 5. And then we have 4 elements. So start with just 0 elements, first elements. 0, 1, 2, 3, 4, 5. And each of those cells will mean whether we can satisfy this the target sum of j using the first I element. Whether we can satisfy sum of j with first I elements. So for example, this cell will mean whether, or this cell will mean whether we can use the first element, 1, to satisfy the target sum of 5.
Right.
Which is probably not possible here.
Yeah.
So a question for Dylan.
Okay.
Do you use this 0 element in your DP array usually?
Well, in this case, you could just like,
Or do you just begin with the first element?
well, for this array, I would say like the first, like I guess the first row doesn't matter that much, but the first column, I would set to like, you set it to all true. Because using like, to get a sum of 0, like
Yes.
it always, you can just pick 0 elements, so.
Yes, that's a great idea. Yes, just as Dylan said, because to satisfy the target of 0, we can always satisfy it.
Yeah.
So we can mark them as true for all of the first column. That's very important because the later DP will use that. And the reason that I like to have a 0 row is that,
I guess the rest of them will be false in the 0th row.
yes, you nailed it, exactly. Because using 0 elements, we can never satisfy the sum of 1 or 2, 3, 4, 5.
I guess it makes it easier because when you fill out the rest of the array, you don't have to worry like if you're checking out of bounds.
Yes,
because,
yes. Exactly, that's a very key observation. Yeah, that's why that for every DP problem, we can always have the 0 row and column. That's great. So now we can start with the first one. So this cell means that if we can take the first element to satisfy the sum of 1, so we will face a decision of whether select this element. So at element I, we will choose whether to select it. If we select DP I and J will be, do you have an idea? If we select it.
So this is like the update like formula.
Yep.
Okay, so for example, in the square like 1, 1. There's sort of like 2 possibilities.
Yeah, feel free to write it here.
Okay.
So if we select DP 1, 1, what will this value?
Okay, so the columns are I, so you see that the cell immediately above it, so DP I minus 1 J, you see that's true, then you know this
feel
must
free
be
to
true.
talk into the camera. So you teach
Okay.
well.
So so as I said, there's like sort of 2 possibilities. So the first possibility is you check the cell right above it, and if that's true, this must be true. And the reason is because if you can get to the target using the first like 0 elements of the array, then of course you can also get to target using the first 1 elements of the array, because you don't have to include it.
Yep, so that's the don't select this element. We can always use the I minus 1 element.
Right.
Yep.
So the second sort of possibility is so you're also checking in the row above, but you want to check see, it'd be like J minus, let's say, yeah, nums, so even which number you're on right now, so.
Yep, 1.
Yeah.
I minus 1. It doesn't matter, it's just, yeah, this will be better.
Okay, so basically, the reasoning behind this is, you check the element that's sort of in the row above, but it's like shifted, like you subtract by the value of the current like element in nums that you're looking at. So for example, if we're looking at 1 right now, we subtract 1 from J. So if we were here, we would be looking at this element, and then if we see that the element is true, then this must be true. And the reason for that is if we can get to the target of 0 using 0 elements, then if we include the element we're looking at right now, that increases the target by the value, and it increases the like number of elements used by 1. So that's sort of why you see this J subtracted by the value right here, because you're like adding the value when you include that element.
Exactly.
Yeah.
And for this example, which cell would we look at?
So you're subtracting I by 1, and then you're subtracting J by the value of the like num you're currently looking at, which is 1. So it'd be here.
Awesome. Yes,
Yeah.
exactly.
You see that's true. So this is true.
Yep.
And I guess it's also important to say that like either of these could be satisfied in order to make this true. So it's like an or. So I can just say like or.
Yeah.
Hey, I guess we can try filling out the rest of the row here.
Yes, please.
So using the same, you're checking the same conditions. Here, we first look like 1 cell above. It's false. Then we look 1 cell up and to the left, because the value of the number we're currently checking is still the same. So we look here, it's also false.
Yep.
Both of these two values, they're false. So this is false. And you sort of think about whether that should make sense or not. It does make sense because you're currently only using 1 element so far. So the max, like, I guess like sum you could get is like 1. So this is basically no way to like get a 2. Just only looking at the first element. And similarly, like there's no way to get like 3, 4, 5 for these. So like, all these are false basically.
Yep. Using the first element of value 1, we can never get beyond value 1.
So it's basically like you take the previous row and then you see what you can build from there. So in the previous row, we only had like a target of 0 to work with. So we can only build on that by adding 1. So in the next like row, we can make a 0 and we can make 1, but we can't make anything else.
Right.
So it's basically building on the previous row. So yeah, for this row,
some might ask whether we always look just 1 cell before it, like 1 column before it.
Oh yeah.
Will it always be this case?
So it won't always be like that. So in this row, I equals 2, we're going to be looking at num equals 2. So we're actually going to have to look 2 columns back instead of 1. That's because we want to look for a target that's like 2 less, because we're going to add 2. So for example, from this column we can see that we can make 0 using like 1 element. If we add 2 to 0, we get 2. So that means we can make a target of 2 using 2 elements. So like this cell right here, this would be true. We know that because we look 1 row above and 2 columns to the left. We can make 0 here, so we must be able to make like 2 here.
Exactly.
Now I sort of skipped like a cell here, but this one is going to be true just because we always, no matter what the value of the num is, we always, one of the conditions is always to check just like directly 1 cell above, and that's because that condition corresponds to just not including this like number, just like so. This is going to be true.
Yep.
Then here, this is going to be true as well. That's because in the previous row we were able to build a target of 1 using 1 element. If we add another element to that, we can now make 3, because we're currently looking at the num2, so it was 3. So fill out the rest of these. We can't make 4 because in order to make 4, we would have to have like 2 somewhere in the previous row, but we don't have that, so those are false. Now it's just quickly fill out the rest.
Yeah, still.
So these 3 are automatically going to be true again because we can just like not include the element.
Exactly.
Now this one is actually, it's false because there's nothing here that we can add 5 to get a 4. So that one's going to be false. But then this one is going to be true because we can add 5 to a 0 to make 5.
Can you explain this cell again a little bit?
This one?
Yeah, just the last. Why can we make this 5?
So in the previous row, we were able to make a target of 0 using 2 elements. Now we're currently looking at num equals 5. So we add 1 more element. If we include that 5, we can now get a target of 5. Because in the previous row, we were able to make 0. And then 0 plus 5 can get us to 5. So we're able to make 5. So like if you use the like sort of conditions, we're checking up 1 row and to the left 5 columns.
Right.
Yeah.
This is awesome.
So I guess at this point you could technically like break the like loop or whatever, because you see that we can make like 5. 5 is like what we want. It's like it's like half of the total sum. So yeah, I guess you could stop, but you can also just keep going, like fill out the rest of the table. Yeah, maybe I'll just fill out the rest of the table just to make it complete, I guess. These are automatically going to be true. Now the num we're looking at is 2. So we check 1 up to the left. It's true. This is going to be true. Then the last row, I don't know if that would.
0, 1, 2, 3, 4. Yeah, we don't have 5 elements.
Really need that one.
Yep.
So that's pretty much the table.
So
if this, so once the table is completely filled, you can basically check the bottom right element. So the bottom right element here, that will correspond to using 4 elements to get a target of 5. And remember, that's our original goal. So
This element?
right, yeah.
Yes.
So the element right here, after we're done filling the whole table, we just check if that's true or not. Like I said, it's possible that you could stop earlier, but yeah, this is just gonna be like the general sort of like stopping point.
Exactly.
So yeah, that's how you solve the problem.
Thank you. Okay, here's another question.
Okay.
Is there any room to optimize the space complexity for this function? Based on what rows are we previously looking at? Are we using all the previous rows or just some specific rows?
Okay, well, you're building each row from like the previous.
Do you think we will need like all of those 4 rows?
Yeah, I guess.
Or can we optimize?
So I guess there's a way to only use 1 row. I'm trying to think of, because for example, let's look at the first row. You're looking at num equals 1. So I guess you could say, I just use 1 row, then I fill in num equals 1, so it changes to true, but then there's sort of a bit of problem because if you make this true, then this is also gonna be true, then this is gonna be true, then the whole thing is gonna be true, but that's not what we want, because we're not allowed to use one element like more than once in the partition. Like,
right,
we
yes.
can't use like 1 multiple times, this 1 here multiple times. So I think how you could do it is, you basically, you're only using 1 row, but you want to separate the results of this iteration from the previous iteration. So I'm trying to think of how you could do that. So for example, we set this to true here. It's like, it's true, but we don't want that to affect the next values. Like, we only want to change this one to true.
Can you, I like your idea.
Yeah.
Can you describe the problem a little bit more about why will it override or something?
So if we only use 1 row, then we're basically, instead of checking like 1 row up and however many to the left, we're only checking to the left because it's like everything's in the same row. So for example, if we're in this cell, we're looking at num equals 1, so we check 1 back and see that this is true, so then this becomes true. But then the sort of problem I'm encountering is that, yeah, if this becomes true, then we loop to the next one, then this also becomes true. However, that's like not correct. There's no way to make a target of 2 using just 1 element, but our current strategy has produced this like incorrect result because we're sort of like adding 1 multiple times. It's like, to get to 1 here, we use this num equals 1 once, then to get this target 2, we're basically using it twice, which you're not allowed to do. And then if you kept on looping, this would be true, this would be true, this would be true.
Yep.
It's like this 3 here, our algorithm currently says it's true because it's adding like 1 multiple times. It's seeing that, okay, we could make 2 here, so we just add 1 to that. Now we can make 3. So it's incorrect.
Mm-hmm.
So actually, I think the way you could fix this is maybe like looping like backwards or something.
That's a great idea.
Does that work? Okay, let's try
do an example.
try this idea. I think I saw this in a different problem or something, like different Leetcode problem, but so this is still gonna be true. That's the case because everything in this zero column is true. So,
Oh, would you also like to write which iteration?
Sure.
Or checking the first element? Or equals 0, okay.
Okay, so the idea was we want to loop backwards instead of forwards, and hopefully that will solve our problem of getting incorrect results because of repeating an element multiple times. So these will all start out as false first. Okay, so now let's do the iteration. So
this is the same initialization as the previous one. Okay, so we are at the first element right now.
Yeah, we're looking at first element value is equal to 1. So we look here. We start here first because we're looping backwards. So we check if we can make. So we check 1 backwards because the value of the number we're currently looking at is 1. So we're at a target of 5 here. We look 1 back to target 4. We can't make 4. So that means this is going to be false. Okay, so next we're looping backwards. So we go to target equals 4. We look 1 back at target equals 3. This is false, so this.
And do we also look at the same thing? Because this will means if we don't take this element. Like we check both this cell and this cell.
Oh, right. So, yeah, you're right. You would check both. So, if this let's say this 4 cell was already true, then we just keep it true because.
What does that mean?
Sort of means that we can already make it. So, even if we look back and we cannot make the previous one, like it doesn't matter because we can still make this.
Using
I don't know
the elements before this one. Yes, exactly.
That makes sense.
That makes sense.
Yeah, so next, looping to 3. 3 is false right now, and then check 1 back. 2 is also false, so 3 is going false. 2, it's also gonna be false because both these are false. Now when we get to 1, 1 is gonna be true. And the reason for that is we check 1 back and we see that target equals 0 is true. So we can make 0. If we add 1 to that, we can make 1. So the first the thing to notice is this gets us the exact same result as here.
Exactly.
But by looping backwards, we're basically able to avoid this problem of using this same element multiple times. Now, for my intuition behind that, trying to think of how you would explain why exactly this works.
that because all the numbers are positive, so for example, if whether we can make value of 5, we will subtract the current value.
Right.
And we will only loop to the things before it and not things after it. And because we update from here, the previous things will not be updated before.
That's right. So
would you like to maybe explain it again?
When we're looping forwards, the values of previous results will affect the future results since we're looking back. But when we're looping backwards, there's no way for like these results to affect these results because we're not looking forwards. We're always looking backwards. And that's like because of what you said, because we're always subtracting a positive integer.
Right.
So yeah, I guess that's the sort of intuition behind what that works. When we loop backwards, our results here are not gonna affect our results here. So like I just, for like a more concrete example, like if we said like 3 to be false, then we're trying to calculate the value at target equals 2. Like we're never gonna look forwards to target equals 3 or 4 or 5. We're only gonna be looking backwards here. And that's what we want. We don't want our previous results to affect like the future results.
Exactly. I love the explanation. Just to clarify, so if we finish updating 3 from here.
Yeah.
And when we are on number 2, those updated value will not affect us.
That's right.
Because at 2 we will only look behind.
Yeah.
And those values are still the previous iteration's values.
Yeah.
That's nice. So now, what's the time complexity before, and what's the time complexity now? And what's the space complexity?
The time complexity should be the same because even though like we only have 1 row here, we're still doing the same amount of loops. So I guess the outer loop we're doing is we're looping for each of these nums right here. So let's say the length of the array is like n or something. So we have like n of n loops. Like our outer loop is looping n times, and then in the inner loop we're like looping backwards across every possible target like value. So the length of this, like the number of target values we're checking, that's determined by like half of the total sum. So for example here our total sum is 10. Our target is 5, so we're gonna be having a loop of like 5. I guess it's technically 6 because we have this like 0 column, but yeah, it's basically 5. So let's say you call the like target like M or something. So that's like basically the time complexity. So it's like O of n times m. So
M, could you maybe write M is the like target sum divided by 2 or something? Yeah, that's good. Amazing.
okay. And then I remember like in the Leetcode question, it specified like it has some bounds for these like things. So I think the length of the array, it was like 200 or less or something.
Yep, yep.
So, and then forget what like the bounds for like sort of the total sum of the array was. I think it was like each element was between 1 and 100 or something.
Yep, yep, yep.
Something like that. So, I mean, theoretically, you could have like 20,000.
20,000, yeah.
So that's 200 times 20,000. That's actually like not too good. It's like
Yeah, it can work.
I'm not sure you can do better though. But
Yeah.
maybe there's some further optimizations you can make, but
It's
I don't
a
think
lower bound,
yeah,
I think.
I don't think there's like a linear solution to anything where like just an O of n solution or something like that. I don't think there's a way to do that. I'm not sure, but okay. So that's the time complexity. So the space complexity for this like optimized like solution, it's just O of m. We only have like one array. It's a 1D array. There's like pretty much m elements. All right, it's m plus 1, but since it's like big O, like the plus 1 doesn't matter, so it's just O of m.
Yep.
Compare that to here. It's a 2D array. This is the space complexity of this is like O of n times m. So it's like the same as it was the same as the time complexity. So yeah, this is a lot better in terms of space complexity.
Would you like to write down the time and space for this?
So, sure.
Yep, we see a difference in the space complexity for sure.
Yeah. Yeah, so it's a pretty interesting problem. I think there's some equivalent problems. I mean, this problem is basically equivalent to like find like, oh yeah, it's like this observation right here basically. So like, anytime you have a problem, you're trying to find a subset that's equal to a given sum. Like, it's pretty much the same problem. So yeah, this is like very useful. This like DP pattern is very useful to know for like these kinds of problems, and also this like looping backwards like trick or whatever, that's useful especially when you don't want to include an element multiple times or like consider it multiple times. If you, let's say you like modify it, like you allow an element multiple times, like then I think looping forwards, that would work. Right. If we're allowing you to. So I think there's like a coin change problem or something. It's like you have some coins and you're trying to, like, let's say it's like pennies, like dimes, and nickels or whatever. You're trying to make like $1 or something. Then, and the problem says like you can use like one coin multiple times. Then you would be able to loop forwards. I think, yeah. I think that all these problems they're like different types of like what's it called, like knapsack type problems, right?
Knapsack, yeah.
There's like a lot of different types.
Exactly. And for that, if we can choose an element multiple times, can we still loop backward if we use 1D array?
I guess like
I'm also thinking this.
Yeah.
Wait, probably the forward is pretty good, I think.
Yeah.
So does that consider maybe if I choose one like for 3 times, will that also be included in this forward path?
You're saying we loop forwards, or?
Yeah. So for example, if we want to make the
Yeah.
target sum of 3, we want to make the target sum of 3, we should be able to use 3 ones to make it to 3.
Yeah. So are you putting a limit on the number of ones, or are you just saying like?
Oh, we can use like an infinite time.
Okay. So then, I believe looping forwards, it does work.
Yeah, maybe can you give an example
okay.
of? I love your idea of that. This looping forward means counting each element multiple times.
Yeah.
I like this idea.
It's not really my idea. Like these problems are kind of tough. Like sometimes I just have to search up like a solution, but so yeah, it's not really my idea, but it's like
sometimes hard to think through this.
Yeah. So we have this like coin change example. So again, we can always just make 0 because we just not include any of the coins.
Yeah.
Now for 1, we can make that. We look back 1. See that's true, so we can make 1. To make 2, we can make that as well because we basically use this 1 like twice. Look back once. We see we can make 1, so now we can make 2. And then we can make like 3. Like, we can basically make any value now. Like, yeah, I guess this isn't the best example because if we have a coin with 1, like we can pretty much make anything. So.
Oh yes.
But I guess like a different problem is like instead of asking can you make the given, I think I saw this like problem on Leetcode. It's like instead of can you make the given sum, it's like how many ways are there to make the given sum. So then I think I remember like instead of a Boolean array, it's like you just have integers. I just like show that.
Yeah,
so,
sure.
I don't know.
Of the extension part.
Yeah, so to restate the problem, so now we're trying to figure out how many ways are there to make a given sum. Let's just say the sum is, we're trying to make 5. See how many ways are there to make 5. Like, let's say it's 5 cents. How many ways are there to make 5 cents using like 1 cent, 2 cents? Is that 5 cents? So the first element in our array, like a target of 0, that's gonna be 1, I believe. Yeah, 1, because there's exactly 1 way to make 0, and that's by not including any of the elements.
Yep.
I mean, unless you had a coin that's worth 0, but that doesn't really make sense. So.
Yeah.
Okay, now we look at how many ways are there to make 1. So now instead of doing some like Boolean type operations, like we're working with integers now, like counts. So when we're calculating how many ways are there to make a target of 1, we're still gonna look back by 1 because we're gonna look back by 1 because that's the value of the num we're currently looking at. But now, okay, I think looping forwards should still work, but okay, so this is now gonna be 2. The reason is because if there's 1 way to make a target of 0, there's gonna be 2 ways to make a target of 1. But that's, given that we're only looking at this element so far right now, we're like, we haven't looked at any of the other ones yet. So just using this 1, through now, wait, is that right?
many ways to make the value of 1?
That doesn't seem quite right. There should be one way.
Yeah, there should be one way.
Yeah, I don't think it's right. I'm trying to think through, like, okay.
So previously we were initialized to all 0. Because using 0 coins we cannot make. We have no ways
right,
of
yes.
making it.
Okay, I should put all these to 0 at first. So I think I made a mistake there. So I think what I should have done is you basically take like the sum of these two, I believe. So it's sort of like what we were doing previously, but previously we had it like or.
Right.
Now we have a sum. So to do this example, like we're currently calculating target of 1.
And using only the first element.
Currently there's 0 ways to make like a 1 right now, but there's one way to make it 0. So using that we can now make 1 because we can add the value of 1 to the value of 0. So let's say this was like 2 instead of 0. So if this was like a 2, then when we update it, it's gonna become like 3, because we're saying like there's one way to build a target of 1 from a target of 0, and there's 2 ways where we already are at a target of 1. So that's sort of why we're gonna add them. So yeah, it's like sort of similar to what we were doing previously, but we're adding integers instead of doing like or. So.
That's great.
So I think that should give us like correct answer for all these. I'm not 100% sure.
Would you also like to help us write out the formula for this DP?
Sure. Wait, that's wrong. It should be like, this is basically plus equals. Like, maybe that's like confusing. What am I doing? This is a 1D array. What am I doing?
We can write the 2D first and then also write a 1D.
Sure. Okay, if we were to do a 2D array solution. Yeah, I guess it should be like nums I minus 1, but that's not that important.
Yeah.
Okay, so this would be the update, like formula, the update rule, if we were doing a 2D array solution, just like we had here. But when we like sort of optimize the space complexity, like to a 1D array, this formula it becomes a bit simpler. We can just do like so this plus equals is kind of just like a shorthand. It's like a shortcut for saying dpj, the jth element of dp is going to be equal to like itself, then plus like the j minus num element of dp. So for example, if we're looking at j equals 2, or we're looking at a target of 2.
And that means filling the target value of 2 with only the first element.
Right.
And how many ways to do
Yeah,
that.
yeah. So using this formula, it's gonna be, we're just gonna basically increment it by the value 1 back. We're gonna increment this 0 by this this 1 right here. We're looking 1 back because, like, again, we're currently at num equals 1. So we become 1. Then do like the same thing. Like, all these are gonna become 1 basically because we're only using this like 1-cent coin right now, or whatever. We're only looking at that one right now. So if you think about it, like, this should make sense because there's like no other coins we can use, so it has to be only one way to make it, and that way is going to be just using, so for example, there's only one way to make 4 cents with a 1-cent coin because we can only use that coin and we basically use it 4 times.
Right.
So that's how this row or this array would get updated for this first like iteration when looking at num is 1. So now let's do num equals 2.
Oh, hi.
Yeah. Oh, I guess you're busy. I guess later.
No. We are working on the dynamic programming.
Yes, the lecture, right? Yeah. Okay.
We are just solving it, the last part. Roy?
Yes.
Yeah, Faradon.
Faradon, yes, I know. I think we were in that
And,
class together.
Dylan?
I'm Dylan.
Hi.
Yeah.
Nice to meet you.
Hi.
Yeah, feel free to say hi on the camera. We're just recording.
Wait, where's this recording going? It's like,
Just for, I think anyone in the ICPC wants to see this problem solution.
Alright.
Roy.
Alright. Yeah, this video is already going a lot longer than it's okay.
Yeah.
So we're checking num equals 2.
Yeah, it's okay. We're just.
So when we're looking at num equals 2, so we're gonna actually start the loop here at target equals 2 because remember we're looking back to, so if we started the loop like here, target equals 0, we're looking back, but there's nothing there, like we're going out of balance in the array.
Right.
That basically corresponds to the fact that like there's like 0 ways to make negative numbers, so if you were to continue this array to the left, it's all zeros, so I mean you could, yeah.
Maybe I equals to 1. Oh, okay.
So technically you could use our same update formula, but you're adding 0 basically.
I see.
So these two stay the same. Now target equals 2, this is gonna change. So using our update formula.
Would you like to use maybe the other pen and write the new?
Okay, yeah, sure. So using our update formula, 1 plus 1 become 2.
And the previous are still the same values?
Yes.
Gotcha.
Maybe, okay. Now for 3, we look backwards 2. See a 1, so this one here plus that one, 2. Now for 4, we look back to, and we're gonna see a 2 there, because I'm writing like 2 numbers here right now, but in the actual array, like there's only be 1 value here, and that's gonna be our updated value, which is 2. That's the value that we just calculated. It's 2. So we look at this value, 2, and then we add it to this 1 right here. So now it's 3. So yeah.
And that means like we want to make the target 4.
Yeah, using just like 1 and 2. So
which cells are we checking? Would you like to draw?
Yeah, so when we're calculating this target 4 right here, we look back 2.
Back to.
So, and then we see a 2 here. We don't see a 1, we see a 2.
Right.
And actually, that's like, I guess you would need to use a forward loop here, because to use a backwards loop, like, because in this case, you want the previous values to, like, inform the next values.
That makes sense. And why does the answer of 3 make sense here?
Yeah, so this is a pretty simple example, so you could just write out all the possible ways to make 4. So you have 4 equals 1 plus 1 plus 1 plus 1. You also have 4 equals 1 plus 1 plus 2. You get 4 equals 2 plus 2. Now, 1 plus 1 plus 1 plus 1, that sort of corresponds to this value right here. Because this is the way we found to make 4 using only num equals 1.
Oh, yes, exactly.
But these two correspond to like this sort of value 2 right here. So you sort of like draw parentheses, like these are the 2 ways to make 2. Now we're adding 2 to both of those. That gets us 4. These 2 ways to make 2, it like corresponds to like right here. So yeah, this way to make 4, that was like, we already knew that from sort of the previous iteration, but now we're adding on these 2 new ways to make 4, and they both come from adding 2 to 2.
It comes from how many ways we can make 2.
Yeah.
Which are 2 ways. Right.
Okay,
This is
so
awesome. I love the parentheses. Awesome.
Yep, so now number of ways to make 5 using only 1 and 2. Also gonna be 3. So we're taking 2 plus 1. Okay, now there's one more iteration left.
Okay, yeah, just one more.
It's 5, and we actually
Here's this, and now the previous iteration.
And for this iteration, like num equals 5, we actually only check 1 target, and that's 5, because the values of these, like 0, 1, 2, 3, 4, these targets, the values are, number of ways to make them are all gonna stay the same, because we're using 5. So if we were to make a value of 4 and we're using 5 in there, that must mean like we had a -1 plus 5, but there's 0 ways to make -1, so
Exactly.
these all stay the same. And then this one is gonna be, we look back 5, so you see a 1 there, so 1 plus 3, that's 4. And then you're basically done. So
we just check the last cell.
I guess I could, these all stay the same.
Right.
Okay. So we're basically done. Now we just check the last element of the array. 4. So there's 4 ways to make 5, and then you could sort of verify that by writing out all the ways, but
Yep, that makes
works
sense.
out.
Thank you so much.
Yeah,
This is very clear.
No problem.
Yay, we solved the problem.
Let's go.
Yeah, thanks, Roy, for comments.